Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now if you find my videos interesting and important to your studies, also please don't forget to subscribe. So here is a portion of distributed forces. So you must first master derivation of formulas for volumes, areas and arcs or lines, and also familiar with them. And this part will be to enhance your thinking skills, especially in locating centroids of volumes, areas, and arc lines, which are necessary later in analyzing a system with distributed forces. Level 21. The mass per unit length of the cylinder rod varies with position according to density equals density sub O quantity 1 minus x over 2, where x is in feet. Determine the location of the center of mass of the rod. So here is the given figure. So take note that the density varies with the distance according to this equation here. So if we consider a differential element at distance x from the left end, which is the origin, so by symmetry, by the way, barred y or yg is equal to 0. So with length differential x and their acts, this is a differential element which is considered a point. This is also the mass center of the differential element, and its value differential mass is density times differential x, because the density varies with x. So by Varignon's theorem, let's compute for the mass by integrating this density, this differential mass. So mass equals integral from 0 to 1 of differential mass. So mass is integral 0 to 1 of rho sub O 1 minus x over 2 dx. So mass is density O x minus x squared over 4 from 0 to 1. Therefore, mass is rho O quantity 1 minus 1 square over 4 minus lower limit 0. So 3/4 of rho sub O. That's the mass of this slender rod. And it's the position of that mass from the left is denoted by xg. So by Varignon's theorem, mass times xg equals integral of x sub c differential mass, where x sub c is just x because we consider differential element and the centroid is located, or center of gravity is located x distance from the left end, and differential mass is given by this expression here. So 3/4 of rho sub O xg equals integral of x quantity rho sub O quantity 1 minus x over 2 dx. So cancel out rho sub O, and take note that if we expand, the first term is x, the second term is x squared over 2. So 3/4 of xg equals x squared over 2 minus x cubed over 6, because the second term would be x squared over 2, so the integral is x cubed over 6 from 0 to 1. So 3/4 of x sub g equals quantity 1/2, 1 squared over 2 minus 1 cubed over 6 minus lower limit 0. So 2/3 divided by 3/4 is 4/9 feet. So that's the location of the center of mass of this rod. Level 22, determine the x-coordinate of the mass center of the tapered steel rod of length L, where the diameter of the large end is twice the diameter at the small end. So this is the given tapered steel rod of length L. So for the solution, we know that the location of centroid of a cone is 1/4 of its height from the base. So if we extend this to form a cone, then because the diameter here is L, so let's extend so that we'll have a big cone, then remove this small cone. The length of this cone should be equal to L also, so that L as 2D is equal to 2L as to 2D, which is L over D. So therefore the length of the extension is also L as shown. Then we treat this tapered steel rod as volume of big cone less volume of this imaginary small cone. Then the location of the volume of big cone, since we know the location of the centroid of a cone is 1/4 of the total length. So the total length is 2L. 1/4 of 2L is L over 2. So this distance is L over 2. So this distance from the reference origin is also L over 2. So that is L over 2 because this is L over 2 supposedly. Or 1/4 of the total height. Likewise, if we consider the small cone, the volume is denoted by a small v, and its location, the centroid or center of gravity, is 1/4 of L. So that's L over 4, but if this is the origin, it lies to the left, so that is negative. So the volume is volume of big cone minus volume of this small cone. The volume of cone is 1/3 area of the base times height or length, and for the big cone it is pi, the radius is d, so pi d square times 2L divided by 3. Pi area of circle, the radius is d because the diameter is 2d, times height 2L over 3. Pi diameter pi radius square or pi d square 2L over 3. So it is 2/3 pi d square L. The volume small v is pi, radius is 0.5 d, quantity square, the length is L, the height is L, divided by 3. So 1/3 pi 0.5 d, quantity square times L. Simplifying, that's pi over 12 d square L. Therefore, the volume, the net volume or the volume of this tapered rod is 2/3 pi d square L minus pi over 12 d square L. And simplifying, it is 7 over 12 pi d square L. So applying Varignon's theorem, let us say the net volume acts here and its distance from this reference is xg. So volume 7 over 12 pi d square L times xg is equal to volume of big cone 2/3 pi d square L, its distance is L over 2, minus volume of small cone pi over 12 d square L, its distance from here is negative L over 4. So cancel out pi d square L. So 7 over 12 xg equals L over 3 plus L over 48 after we cancel pi d square L. So L over 3 plus L over 48 divided by 7 over 12, we can now solve x sub g, and it is equal to 17 over 28 L. So that's it for this level 22 problem. Level 23, a composite beam is constructed by bolting 4 plates to 460 by 60 by 12 mm angles as shown. The bolts are equally spaced along the beam and the beam supports a vertical load. As proved in mechanics of materials, the shearing forces exerted on the bolts at A and B are proportional to the first moments with respect to the centroidal x-axis of the red shaded area shown respectively in parts A and B of the figure. Knowing that the force exerted on the bolt at A is 280 newtons, determine the force exerted on the bolt at B. So here is the given figure, and this is an application on shearing stress or shearing force from mechanics of materials. And since that is the subject after this course, so let's just apply it. As stated in this problem, the shearing force is proportional to the first moment of areas of these shaded red areas with respect to the centroidal x-axis, which is obviously by symmetry here through C, horizontal line through C. So for part A, the shaded area is just this, and its moment about C can be easily computed. For part B, we have to consider also this moment of this additional angle. So it is the first moment of this flange here with respect to the centroidal x-axis plus the moment of these two angles with respect to this centroidal x-axis. But we have to locate the centroid of each of these two angles so that we can compute the moment of the contribution of these angles with respect to the centroidal x-axis. So shear force, so let's call this y1, the distance of the centroid of this shaded area with respect to the neutral axis, and this is the centroid of one of the angles, and its distance from the neutral axis from this centroidal x-axis is denoted by y2, and its distance from the bottom of this rectangular plate as yc2 as shown. So shear force is proportional to the first moment of area, which is denoted by Q, and this is the constant of proportionality. Therefore, the constant of proportionality is shear force over Q, which is the shear force in bolt A over Q, QA, and shear force in bolt B over Q sub B. So for QA, so Q is area times Y, where Y is distance of the centroid of the area to the centroidal axis. So Q sub A is 300 times 12 times quantity 450 over 2 plus 12 over 2. So the distance from centroidal x-axis to the bottom edge of this rectangular plate is half of 450, then plus the location of the centroid of the plate, which is half of 12. So that's the distance of this area, centroid of this area from the centroidal x-axis. So QA is equal to 831,600 mm square. Then Q sub B is QA plus area 2 times area of angle times y2. So let's enlarge and magnify this angle so that we can compute y sub c2 after we compute y2. After that, we can compute y2. So this is the enlarged or magnified angle. So 60 by 60 by 12 thick. Therefore, it is there. This shaded area is simply area of big square, 60 square, minus area of this imaginary square, which is 48 by 48, where 48 is 60 minus 12. So this is 60, the thickness is 12, so 48. The location of the centroid of the 60 by 60 square from the from this edge here is half of 60, so 30 as shown, 30 mm, while the centroid of this square 48 by 48 is half of 48, 24 plus 12, so 36 as shown. So the centroid of this shaded area is, the distance is denoted by y sub c2, and let's call that y sub c2, which can be solved by Varignon's theorem. So the area is 60 square, area 2 is 60 square minus 48 square, and it is 1296 mm square. And by Varignon's theorem, 1296 times y sub c2 equals 60 square times 30 minus 48 square times 36. From there, we can solve y sub c2, which is equal to 58 over 3 mm. Having computed y sub c2, we can now compute the distance of the centroid of the area of the angle to the centroidal x-axis, and that is y2. So y2 is 450 over 2, or 225, minus y sub c2. So y2 is 225 minus y sub c2, where 225 is half of 450, then 58 over 3 is y sub c2. So 617 over 3. Therefore, QB is 831,600. So that's the Q of this rectangular plate, plus 2 times area of the angle 1296 times distance of the centroid of that angular area to the centroidal x-axis, which is 617 over 3. So Q sub B is equal to 1364688 cubic mm. Substitute into this formula where shear force at A is 280 and QA we have computed it, then SFB unknown, Q sub B is equal to this. So 280 over 831,600 equals SFB shear force in bolt B over QB 1364688. So we can now solve shear force in bolt B, and it is equal to 459.5 newtons. Level 24, determine the y-coordinate of the centroid of the shaded area in terms of R1, R sub 2, and alpha. Also show that as R1 approaches R sub 2, the location of the centroid approaches that for an arc of circle of radius R1 plus R2 divided by 2. So here is the given figure, and this is sector, big sector minus small sector, the shaded area. So the location of the, let's call that theta, this is also theta here, and theta is 90 degrees minus alpha, or in radians pi over 2 minus alpha. And the location of the centroid is there. The general formula for y sub c is 2r sine theta over 3 theta, if you can remember. So area is 1/2 radius squared times central angle. Since the central angle is double that of theta, then we can also use radius squared times half of the central angle. So that theta is 90 degrees minus alpha, or pi over 2 minus alpha in radians. So area 2 is R2 squared times theta. Area 1 is R1 squared times theta. So therefore, the net area is R2 squared theta minus R1 squared theta. If we factor out theta, then we have R2 squared minus R1 squared quantity times theta. Then by Varignon's theorem, R2 squared minus R1 squared theta times yg equals R2 squared theta times 2R2 sine of theta over 3 theta minus R1 squared theta times 2R1 sine theta over 3 theta. So cancel out theta and simplify. R2 squared minus R1 squared equals yg equals 2 sine theta over 3 theta times quantity r2 cube minus r1 cube. So r2 square minus r1 square, yg equals 2 sine of 90 degrees minus alpha over 3 times pi over 2 minus alpha times r2 cube minus r1 cube. So take note that sine of 90 degrees minus alpha is cosine of alpha. This is just cosine of alpha. So yg is 2 cosine of alpha over 3 times quantity pi over 2 minus alpha, or pi minus 2 alpha all over 2 after we simplify this. Then quantity r2 cube minus r1 cube divided by r2 square minus r1 square. So simplifying, yg is 2/3. This is the 2/3 here, or this 2 becomes numerator, 2/3 of quantity r2 cube minus r1 cube over r2 square minus r1 square. This is it. Then times 2 cosine alpha over pi minus 2 alpha. So that's why yg is given by this expression. So let's now proceed to this second part, that as r1 approaches r2, the location of the centroid approaches that for an arc of a circle with radius r1 plus r2 over 2. So yg is, we copy this first, over r2 square minus r1 square times quantity 2 cosine alpha over pi minus 2 alpha. And for the arc, yg is r sine theta over theta, remember that. And let's prove the result here. So yg is 2/3 quantity r2 minus r1 times r2 square plus r2 r1, or r1 r2 plus r1 square. After we factor this difference in 2 cubes and difference of 2 squares, the factors are r2 minus r1 times r2 plus r1, and the rest will just copy. So cancel out r2 minus r1. So yg is 2/3 of quantity r2 square plus r1 r2 plus r1 square all over r2 plus r1, then times quantity 2 cosine alpha over pi minus 2 alpha. So because r1 approaches r2, we imagine that r1 is approximately equal to r2. So the numerator becomes, so we have 2/3 of r2 square plus r2 square plus r2 square, because we just set r1 equal to r2. Then r2 plus r1, we just leave this at this. Then 2 cosine alpha over pi minus 2 alpha. So this is the result, because as r1 approaches r2, then r1 is approximately equal to r2, and r2 is approximately the average of r1 plus r2 over 2, because this is approximately equal to r2. Then we have yg equals 2/3 of 3 r2 square over r2 plus r1 times quantity 2 cosine alpha over pi minus 2 alpha. So cancel out 3. So yg is 2 times r2 square over r2 plus r1, then quantity 2 cosine alpha over pi minus 2 alpha. So we replace r2 by r1 plus r2 over 2. So 2 quantity r1 plus, or r2 plus r1 over 2, then quantity square over r2 plus r1, then quantity 2 cosine alpha over pi minus 2 alpha. So we can cancel r2 plus r1 here. So what is left here is r2 plus r1 over 4. So yg is 2 quantity r2 or r1 plus r2 over 4. then quantity 2 cosine alpha over pi minus 2 alpha. Finally, we can cancel 4 and write yg equals r1 plus r2 times quantity cosine alpha divided by pi minus 2 alpha. So that's the value of rg, yg, and let us show that this is also the centroidal location of an arc of a circle with radius r1 plus r2 from this general formula here. So replacing r by r1 plus r2 over 2, then sine of 90 degrees minus alpha, which is cosine of alpha over pi over 2 minus alpha. So if this 2 is distributed here, then this denominator becomes pi minus 2 alpha, which is now of this form. So yg is r1 plus r2 times cosine of alpha over pi minus 2 alpha, which proves that they are equal. So therefore, this statement is correct. Level 25, use the method of composite areas to calculate the centroidal coordinates of the plane region shown. So here is the given figure. So for the solution, the plan is we first compute the area of this unshaded region, and after computing the area of this unshaded region, we also compute the location of its centroid from the x-axis. Then, having found the area and the location, then we consider the entire area of the semicircle less this so that we can locate the centroid, y-coordinate of the centroid of this symmetrical shaded region. Because the region is symmetric with respect to the y-axis, therefore barred x or x sub g is 0. We only need yg or barred y. So for the area of the unshaded region, it is equal to the area of this sector minus area of this triangle. So let's focus first on sector and triangle. So this distance is, because the radius of this arc is 60 mm, this is 60 mm, and the angle is 30, so 60 sine 30, 60 times sine 30 is 30 mm. The calculation is not shown, but I mentioned it. You just use your calculator. So call this theta, which is 60 degrees. That's also theta, 60 degrees or pi over 3 radians. Then area of sector is 60 square radius square times half of the central angle theta, which is pi over 3 radians, 60 degrees or pi over 3 radians. So area of sector is equal to 1200 pi mm square. Then the area of triangle, because the unshaded area is area of sector minus area of triangle. The area of triangle is 1/2 product of adjacent sides times sine of the angle included. So area of triangle is 1/2 60 square sine of 120 degrees, 60 times 2, so 120 degrees. So area of triangle is 900 square root of 3 mm square. So the unshaded area therefore is 1200 pi minus 900 square root of 3, and that is equal to 2211.07 mm square. The location of the centroid of the sector is in general 2r sine theta over 3 theta. So y sub c of sector is 2r sine theta over 3 theta, where theta is 60 degrees or pi over 3 radians. So 2 times 60 sine 60 over 3 times pi over 3, and it is equal to 33.08 mm, while the centroidal location of this triangle is 2/3 of 30 from the vertex, so it is 20. Not shown, but it is 2/3 of 30, so 20 mm. Then apply Varignon's theorem to locate the centroidal coordinate of this unshaded area. So net area 2211.07 y sub c of the unshaded area is area of sector, y of sector, y sub c of sector minus area of triangle, then y sub c of triangle. So from here we can compute the centroidal location, y coordinate of the centroid of this unshaded area, and it is equal to 42.302 mm. Next, we consider area of semicircle and this unshaded area to locate the y coordinate of the centroid of this entire shaded region. The area of the semicircle is pi 80 square over 2. Pi over 2 radius square, so 3200 pi mm square. Then the location 4r over 3 pi because it is semicircle. The y coordinate 4 times 80 over 3 pi is 320 over 3 pi mm. So by Varignon's theorem, the area net is 3200 pi area of semicircle minus area unshaded 7842.03 mm square. Then by Varignon's theorem, 7842.03 times yg equals 3200 pi times 320 over 3 pi minus 2211.037 times 2211.07 times y sub c of the unshaded area 42.302. So we can now solve yg equals 31.6 mm, and remember xg is 0 by symmetry. So that's it.